Hi everyone. I think it's time to get started, otherwise we'll be running late. So thank you very much for joining the session. Hope you had a nice break, good lunch, and hope you're ready for this presentation now. So I would say, for the sake of time, let's get started immediately. So just very quickly, who am I? So my name is Michel. I'm a researcher at the Cambridge Center for Alternative Finance, which is an academic research center based at Judge Business School at the University of Cambridge. So I'm leading our cryptocurrency and blockchain program. So what do? We primarily do what we call benchmarking studies. So we reach out to companies in the space, but also regulators, central banks, any type of public sector institutions, and get survey data from them, which we then combine with publicly available data sources to present an empirical picture of what's going on in these ecosystems. So we do it both for public blockchains and crypto assets. So this is our inaugural report that we published last year in April, coincidentally just a week before prices started skyrocketing. So it was literally outdated the second it came out. Coincidentally, just yesterday we published an update to this study with 180 different participants from 47 countries. So it's freely available on our website if you want to have a look. But we also do the same for enterprise blockchains, which is more the topic, I would say, of this conference. So we published the inaugural report in September last year. We had over 100 companies, from startups to established corporations, but also regulators and central banks. So we're working also on a second update for that. Server is already closed. Maybe some of you have actually participated. So we plan to publish that study around February, March next year. But so today I want to talk about this particular study, which I came up with in August of this year. And that's more like a theoretical, conceptual view. So it's not based really on empirical data. So we assembled a group of a dozen researchers and industry experts to tackle what we think are two major problems in the space right now. So the first problem I think everybody can agree with is that there's fuzzy terminology. People use the same words but mean different things, or they use different words to mean the same thing. So it risks really that people risk talking past each other, which is not great. So here's just one selection of some of these terms. I guess most of you are familiar with them. Now, they can mean the same thing. They can mean completely different things. It really depends who you're talking to. So what does blockchain generally mean when people talk about it? So really at its most basic, people refer to it as a data structure. So really just blocks of data that are chained together using cryptographic hashing functions. Now that is generally not really what people are really excited about when you talk about blockchain. So another interpretation of blockchain could be multi-party consensus systems. So you have multiple entities that together need to reach agreement over some shared set of data. Now, blockchain is also often used just to refer to common data standards, and actually that's a very good rule of thumb. So if you read a press release and you can replace the term blockchain by common data standards, then you can be pretty sure that this is exactly what this project is all about. And then, of course, finally, it's a very handy buzzword that drives marketing, sales, and a lot of excitement. So when we say DLT systems, we actually refer to multi-party consensus systems. Now, why DLT systems and not blockchain? Well, because we've seen the emergence of blockless blockchains, of chains of transactions, and distributed ledgers and so on. So we wanted to have a more generic term that kind of like fits all of these categories. Okay, so what are DLT systems then? So let's imagine we have four entities that each maintain their own fully validating nodes and as well their own version of a database, which we're going to call a journal in this context. And that's beyond the accounting meaning of the term. So each of those nodes maintains their own version of that database. So what is the ledger now? Well, the thing is, people think blockchain is a database, but actually it is rather a mechanism for synchronizing these individual databases so that they are most of the time in sync, so everybody has the same shared view. Of course, the most important part, that there should not be one central authority or server in the middle to guide these synchronization efforts. And so the ledger in all of this is that over time, all these individual instances maintained by each node locally and individually, so the journals, should converge towards one single shared view that everybody agrees upon, which is what we call the ledger. So the ledger itself is actually something that doesn't really exist. It's more an intangible, emergent thing that actually really emerges out of the efforts of the system of synchronizing these individual journals. So just to walk you through how that generally works, 5-step process. So you have end users that want to create transactions. So there's different means of doing that, different types of broadcasting it. So I won't bore you with all of the different possibilities. But let's say they're end users who broadcast unconfirmed transactions to the network. So then we've got special nodes in that network, which we're going to call auditors. We could call them fully validating nodes as well. What they're going to do is they're going to pick up these unconfirmed transactions, verify whether they comply with the protocol rules that these nodes are enforcing. And if that's the case, they're going to put it into what we call a log. In Bitcoin, that would be called a mempool. And that's nothing else than really just a set of unconfirmed transactions that each node maintains. So a log can be different from one node to another, depending on when they see transactions coming in. Now we've got another type of special nodes, which we're going to call record producers. In Bitcoin, it would be called miners. So what those nodes do is that they go into their own log. Then they select, or arbitrarily select, a set of unconfirmed transactions and put them into a candidate record, or in Bitcoin, a candidate block. They then broadcast that candidate record to all nodes that they're connected to. So now the second phase of validation starts. So each node, again, checks whether the candidate record he receives complies with the protocol rules. And if that's the case, they're going to add it to their own individual journal. Now, after some time, ideally, a ledger should emerge so that everybody now has in their journal the same candidate records, which then means that the transactions inside their record are being finalized. So what is the difference, again, between the journal and the ledger? Well, the journal is at the individual node level. So each node has its own journal, which can be provisional and can sometimes be an imperfect copy of the ledger. So I might have, at some point in time, a different version of the journal. So my journal looks different than yours. But over time, through the efforts of that system, all our journals should converge towards the same shared view, at which point we have the ledger, which is really at the global system level, so the globally agreed upon set of data. Now, there are different ways of getting to that point when something is being finalized, and that depends really on system configuration, so we won't go into that in detail here. But just saying that this is different for each system. Now, there are a lot of projects that claim to be blockchain-based or blockchain-inspired, or, there's like lots of these, how can I say? Well, I won't dive into that. But so the thing is, what we wanted to come up with is a set of key characteristics that, in our opinion, an ideal DLT system should fulfill. So first characteristic, what we call shared record keeping, with a particular emphasis on shared. So you should have multiple entities that contribute data or write data to that global data store. If you have just one entity, well, then there's generally no disagreement over the data, so there's no point in using such a system. Second, we've already briefly touched upon it, should be multi-party consensus. If there is only one single entity who decides about conflicting transactions, well, then there's absolutely no need to having such a system. Independent validation is something that often gets overlooked, but we consider that to be actually one of the most important parts of the system, and really with an emphasis on independence. So every fully validating node or auditor should be able to independently recompute the entire state of the system, or at least to get to the same current view, without having to rely on some sort of third party to provide them with the data of doing so. Which means that if you run a node, or if you don't run a node, and you actually have to query somebody else that runs a node for you, well, then you're just as dependent on a third party as if you were querying any centralized database. So if you, as a participant in that network, cannot independently validate it, then there's literally no point, because you still need to trust some third party of doing that. And there might be good reasons for doing that. But really, in an ideal DLT system, you should always be able to independently validate everything. Then we have something we call tamper evidence. So what that means is that it should be very easy for any participant to immediately detect if somebody is cheating, or what that means is tampering with old data, so changing the past transaction history, which is not to be confounded with tamper resistance, what some people call immutability. Now, we don't like the term too much because we think that there's no such thing as absolute immutability. Anything can be changed. So we prefer using the term tamper resistance. And what that means is that in those systems, it should be very hard to change past data. Now, there's different ways of achieving that. So in the case of proof-of-work blockchains, it actually takes you quite a lot of physical resources and financial costs of doing so. Now, in some enterprise blockchains, it might just be the threat of legal actions if you cheat, that somebody will take you to court. So there's different ways of getting to that. Now, why do I say an ideal DLT system should fulfill all of these? Well, because if you apply those 5 characteristics to all the blockchain projects that claim to be blockchain, actually, really most of them do not even satisfy 1 or 2 of them. which again is not necessarily a bad thing. But the problem is just that the term blockchain is just being used inflationary and kind of like creates a lot of confusion and misconceptions about what the technology can actually achieve. So for example, in the report, we actually look at 6 case studies where we apply the framework to as well. So I'm going to explain the framework in a second. So you have, on the one extreme, you have Bitcoin. Then on the other extreme, you have something we call Project X. That's actually a company that's building something, but it's completely centralized. And so they preferred to stay anonymous. And so there's like an entire spectrum. Now, if you apply those 5 characteristics to them, and this is at the time of writing in August, so it might have changed over time, is that actually not a lot of them do satisfy these 5 characteristics. Okay, so now problem number 2, and this is very, very common and creates a lot of problems actually, is that we tend to compare apples to oranges all the time. So generally a conversation goes like this. So there's somebody who walks up and says, well, do you know Bitcoin only processes 3 to 4 transactions a second, while we can actually do 1,000. Then there's another guy who walks up, well, that's cool, nice, but we can actually do 1,000,000 transactions per second and no fees. And then there's a third guy who walks up and says, well, our blockchain 4 of those quantum resistant, and we can scale it indefinitely, and it's fully private as well. Now, the thing is, each of these claims may actually be factually correct or true, but the problem is these metrics are being achieved by engaging in different trade-offs, which are often not disclosed but hidden. So it's really about trade-offs. If you want to compare different systems, you need to understand what trade-offs they choose in order to get to one particular metric. So you cannot compare systems just using one single metric. And why is that? Well, because every single of these systems is completely unique. So it's driven by use case requirements, or at least system design should be driven by use case requirements. What we mean by that is that you shouldn't use a blockchain just for the sake of using a blockchain, but build a system that works to serve that intended purpose. And if that system in the end doesn't satisfy these 5 characteristics, which in many cases it won't, well then that's actually better than having a system that does not do its job very well, but satisfies the characteristics. So it should always be about use case requirements and not just using a blockchain for blockchain's sake. Now, what else is different? Well, you have different design configurations, which we're going to talk about in a second. Of course, you have different governance models, which have a huge impact on system properties, and different actors, which creates different power dynamics. And of course, these actors are evolving over time. So all these systems are always dynamic, which means that if you go back to these 5 characteristics, a system that today might not fit all the 5 characteristics, well, it can evolve into something over time so that it becomes what we call an ideal DLT system. Or the opposite, it might actually regress in becoming something which we don't consider a DLT system anymore. So really, if you study these systems, it should be done on a continuous basis because these are really dynamic and evolving very fast. So what do we do about this? Well, that's why we came up with what we call a conceptual framework for analyzing these systems. So you can take any given system and actually decompose it into its different elements. And then we're going to analyze how these elements, depending on how you configure them, will impact other elements and in the end also system properties. So our framework has 3 main elements. So the first one is what we call layers. So that's the colorful boxes there. There's 3 of them. Now each layer has a set of components, and a component contains a set of logical related processes, which is just a series of actions taken by actors. So all of this is in the report. I'm just going to very briefly explain the layers. So it's very well explained there, over 100 pages, so there's a lot to read. Now, the bottom layer, and I would say the most important layer of any DLT system, is what we call the protocol layer. And what the protocol layer does is that it sets the rules and defines the rules of the system, so according to which the system will function. Now, it's got 2 main components. So the first one, which we call Genesis component, so that is determining which kind of code base you use. Is it based on another system, or is it like a standalone system? Who creates the rules? Who decides on what rules to initiate? Now, once the system is running, you need to have a way of modifying the rules, if you like. So that is what we call the alteration component. So that would be protocol governance, and who has the right to do changes, how are changes being implemented, and so on. Now, the middle layer is what we call the network layer, and that is really where the system comes to life, essentially. So that's the peer-to-peer network that implements the rules which are dictated by the protocol layer. So it's got 3 main components. So first one is communications. So that's first who has the right to access the system, how is data being broadcast across the system, is it universal, is it localized, and who has the right to actually initiate transactions. Then we have the transaction processing component. In proof-of-work currencies, you would probably call it mining. So this is really who has the right to create a record, how do you actually resolve conflicts if there are two valid transactions that are conflicting, and how do you incentivize people to actually participate in that process. And then very importantly, something people tend to forget a lot is the validation component, which means that once we have a record there, how do we actually prevent people from cheating? So how do we validate everything, and after what time can transaction be considered to be finalized and not reversible? And then finally, we've got the upper layer, which is the data layer, and that is really the records, so the records that the system produces, so the actual nature and the meaning of the data that flows through the system. So are you recording things in the supply chain? Are you recording native digital assets? This is all specified by the data layer. So two components, operations and journal. So journal is what does it reference to? We're going to talk about this in a second, but are we talking about fully endogenous references, so things that only exist within the system itself, like cryptocurrencies, or are we talking about things that exist outside of the system, like items in the supply chain? Okay, so no, before that, actually, yeah, just going to walk you a little bit through one example. So the thing is, in our report, we go actually through each of these 18 processes, and we have a set of configurations, just to give people ideas of what potential configurations are. So taking the network access process as an example, so generally, we analyze each of these processes through various lenses. So in that case, it would be openness, so who has the right to actually access it, and then second, how do you access it? So what are the channels to get into the system? And then for each of these lenses, we come up with what we call configurations, so possible ways of actually implementing this. And the good thing about all of this is that we try to keep it fully modular and customizable. So you could add new configurations, you could remove some, it really depends. It should be a dynamic thing, and you can take this entire framework and actually, you're supposed, or you can, add new processes to it, remove existing ones, just so that it fits your particular needs. So, okay, what are the consequences now of all of this, or the implications? I would say this is the most important one in my eyes, and that is that there is a layer hierarchy, which is very important to consider when you analyze such a system. So the protocol layer always trumps the network layer, which always trumps the data layer. Now, to give you an example, you can have a completely open, permissionless data layer, which means that anyone can build their own applications and run them on the system. The problem is if your network layer is relatively centralized, the network layer can at any point in time override any decision taken at the data layer. In the case of miners, for example, it would be very easy to censor all your transactions that relate to your application. So your application, you have the right to do an application, but the thing is, because no miner will include your transactions, your application doesn't work. So miners or actors at the network layer can always override decisions taken at the data layer. Now, the same thing applies to the protocol layer, because that's where we define the rules, right? So if you have a centralized protocol layer where you have one individual or a group of people that can actually decide to change the rules, but then they can at any point in time override decisions taken by record producers or miners at the network layer and at the data layer. So it is very important, if you analyze a given system, that you identify the actors that operate at each of these layers, assess their relative influence, and whether they can actually implement these things there. So there is a layer hierarchy, and that is really important to consider. So there are lots of trade-offs when we come to design configurations. So just to give you a few examples, well, governance has an impact essentially on literally every single elements in your system, so I won't go too much into that. But then network access, depending if it's open, semi-open, or closed, does have implications on whether you need to have a gatekeeper or not, the trust requirements, also the diversity of network participants. Then, for example, you have the broadcast process. Is it universal, meaning that every single node needs to receive and validate and broadcast every single transaction and store it indefinitely? Or is it localized, so a kind of channel model like Hyperledger Fabric uses it, for example, or Corda, that you only actually need to store transactions that you're directly involved in, which then has implications on privacy, but also on scalability and auditability in the end. Similar for transaction processing, so mining, depending on how you do it, it has an impact on transaction finality. For example, proof-of-work cryptocurrencies or DLT systems do not have finality. They just have something we call probabilistic finality, because at any point in time, in theory, you could actually reorganize the chain. It would just cost you a lot. depending on, of course, the proof of work chain. Now you can also have transaction finality in the sense that a group of entities decide that after so many blocks, we will consider that block to be, or transaction in that block to be finalized, which is a completely different security and threat model. Also, incentives, of course. So how do you incentivize people to actually participate in this transaction processing component? And that has implications on whether you need to have a native asset to reward them or not. And then finally, the references, which we're going to talk about in a second. So can your system actually enforce decisions that it takes, or does it rely on some external agents to implement those decisions in the real world? So depending on which design configurations you choose for each of these different processes, and that results in different system properties. And some of them might be more desirable, some less, depending on really what you actually try to achieve. And so again, going back to these trade-offs and so on, it really should be driven by use case requirements. So you should design your system to actually serve your use case. And the thing is, for some, you might want to have certain properties which then come at the expense of some other property. And that is very important to keep in mind, and especially when you compare different systems against each other. Because one system that actually tries to aim for high censorship resistance cannot at the same time have high throughput capacity and low overheads. So it's all about trade-offs. And these trade-offs need to be properly disclosed if you want to analyze these systems and compare them. Okay, so record references. We talked quite a lot now about the infrastructure, so the base layer. Now, what about the things that we're actually recording and trying to reach agreement over? So we came up with a rather simple three-category model, which operates across the spectrum. So on the one extreme, we have what we call endogenous records or references. And those are things that only exist within the boundaries of the system. So they don't exist anywhere else. So good examples of that would, of course, be native crypto assets, whether it's tokens of an application or cryptocurrencies, to have their own blockchain. They don't exist outside of the system. Now, on the complete other side of the spectrum, we have what we call fully exogenous references. And those are things that that only exist outside of the system. So essentially, our DLT system, in this case, just acts as a normal record-keeping system of external facts or events, which, of course, then requires first an oracle to get information from the outside world onto the system, and then very importantly also external agents that will enforce the decision taken by the DLT system to actually enforce it in the real world again. And then we get a very interesting category in the middle, which is just going to call hybrid. And they share actually both characteristics of endogenous references and exogenous references. So one example would be the Royal Mint gold. I'm not sure if you're familiar with that project. But so the Royal Mint, they mint the British pounds, or at least cash. And so what they did is that they came up with a system where they created tokens that gives you the right to actually redeem it for 1 gram of gold. So the thing is, it is endogenous in the sense that the token itself is more like an additional financial instrument that exists on its own and in the form of a token in the system. But it is also exogenous in the sense that if you want to redeem it for the actual gold held in a vault by the Royal Mint, well, then you need to actually trust the Royal Mint that it can redeem that. It's got like both characteristics together. And again, there's like an entire spectrum depending on what these relations and interactions are. So it needs to be analyzed on a case-by-case basis. But so why is this important? I already briefly touched upon it before, but it's really about the ability of the system to actually independently enforce decisions that it takes. So if we just use it for exogenous references, let's say luxury bags in a supply chain, well, so the system itself has no idea what it is recording. So it is just recording data that it needs to trust. And then it takes a decision, let's say, okay, the thing arrived from A to B, but that doesn't necessarily need to correspond to the real world, and the system has no way of actually enforcing that. So it needs to rely on external agents. Now, with fully endogenous things, because they only exist within the boundaries of the system, if the Bitcoin blockchain, for example, says that my Bitcoin are now sent to you, and after a certain amount of blocks is very unlikely to be reversed, well, then there's nobody who can actually change anything about this. No external agent needed for that. The system itself can implement and independently enforce that decision. So a lot of projects we actually look at, especially in the enterprise blockchain world, is mostly about fully exogenous things, in which case the DLT system itself is just a record-keeping system and doesn't really solve much problems, rather than at least compared to other traditional record-keeping systems. So we personally think, well, I personally think that fully endogenous references do make most sense if you're talking about these particular systems. So again, what interactions are required? So we have these fully endogenous ones that only exist within the system, so you don't need to have any external agents. Now for anything, whether it's hybrid or fully exogenous, these things reside in other systems, whether that's the real world, whether that's a database system maintained by a company or whatever, and it requires gateways to bridge the gap between the DLT system and the other system where the things that we're recording actually exist. Okay, so in our report, we have, again, these 6 case studies. So for each of these different processes and layers, we actually compare them in a standardized way using these design configurations, so you can have a look. I can walk you through a few examples if you like. So for example, let's take the code-based creation process. We have 2 lenses, so what kind of code base is it? Does it already exist? Or is it completely built from scratch? And then compare that to whether that code base is open source or not. So for example, you have Bitcoin, Ethereum, Ripple, all built from scratch. They're open source. Anyone can just fork off, create their own system, that's it. Then you have a project called Elastia. Not sure if some of you are familiar with, but the idea is to create a national blockchain network for Spain. So with regulators, big banks, big telecommunication operators, and so on, all being on the same network. So that network is being built on Chrome, which is a private version of Ethereum. But the code base is open source, which means that if there are disagreements over the direction that the project is taking, network participants could always fork off and create their own system with the same transaction history. Which is not the case for those 2 projects, verified on me and our anonymous project, which are built on Hyperledger Fabric, because they chose to keep their particular implementation closed source, which now means that network participants, if they disagree with the governance model, they can actually not just fork off and create their own system. So this is a big difference. Now, another example, if we look at governance and network access, so we have, for example, this one project that is entirely centralized, so it's essentially one company that decides who can enter the network, and it's one single company that decides the rules and how to change them. And we've got verified on me and Elastia, which are kind of like in the middle, so it's closed, but they do something which we call distributed gatekeeping, which means that nodes in the network can collectively vote to actually accept new members. So there's not one entity that acts as a gatekeeper and decides who can enter it, but it's actually multiple entities together that can collectively vote on onboarding new members. And we call that a federation as well when it comes to governance, because there's not one single company who can decide on the rules to change, but there's a set of companies that then again collectively together have to agree on that. Ripple is kind of like an edge case for actually most of these comparisons, so it's always in between. So in theory, it's completely public. Now the thing is, if you actually try to run a Ripple node, the first 30 or 40,000 blocks are missing. Nobody really knows what happened to them, which is really strange. And the thing is, when it comes to governance, officially anyone can fork it, anyone can build their own things on it and so on, but the thing is, in the end, there's a company behind it which has a lot of influence. So we put it somewhere in the middle there. Then, of course, you've got these open permissionless networks such as Ethereum, fully open, there's no gatekeeper, and Bitcoin, which we would even put a little bit higher in the sense that Bitcoin is probably the closest you can get to anarchic governance model, in the sense that you probably never agree on changing anything, which can be a feature in some cases. Why is Ethereum a bit lower? Well, the thing is there's a foundation behind it already, and they have that public figure in the form of Vitalik. Although he doesn't decide everything on its own, he has like huge influence on protocol development. Another example for the network architectures, again, we're going to take network access and then compare that to data diffusion models. So whether everyone needs to validate everything, or whether we use these multi-channel or whatever it's called, there are like different names for that context. So again, Bitcoin, Ethereum, and Ripple network is open. Anyone can run their own nodes, and as a result, because they don't want to rely on some sort of trust, everybody needs to verify every single transaction, store it indefinitely, which is different from Elastia. So Elastia is closed access, but it also has, because it is based on Ethereum, it also has that universal data sharing model. Right now, the network is still in, I think in beta. I think it hasn't even really launched yet, and it was planned to do so beginning of 2018. So let's see, but their plan at least was to onboard hundreds of different companies. Then we've got Verify.me and that anonymous company. So what it is completely closed access, and they use the multi-channel model because they're based on Hyperledger Fabric. Right now for Verify.me, there are 15 different entities running nodes, whereas for the centralized project, there are 3 different entities, but all their nodes are run by the same company in the cloud, which, if you go back to the system characteristics in the beginning, is questionable, but yeah. Finally, last example, transaction processing or mining. So record proposal in this case means who has the right to actually participate in this voting process, so who has the right to become a record producer. And incentives is what is the incentive for people to do so. So Bitcoin, Ethereum, permissionless, anyone in theory can actually mine. And it's primarily based on intrinsic and monetary incentives, which require to have a native asset as reward. Now, Ripple and Verify.me, anyone that is in the network can actually participate as a record producer, but they don't have intrinsic incentives, so it's mostly extrinsic, non-monetary incentives. Although in the case of Verify.me, the record producers actually receive a service fee paid by the company that built this entire project. And then we've got Elastia and this other project. So here, within the network nodes, only a pre-vetted set of nodes are actually allowed to produce records, and also not based on intrinsic motivations. So just to like one last concept, probably. So the thing is, there's like a big discussion about projects being centralized or decentralized. So giving the idea that it's really a binary property. And actually, decentralization is really a multi-dimensional, multifaceted concept. And in order to analyze whether such a system can be considered to be relatively centralized or decentralized, you need to actually take into account lots of different factors. And so, again, going back to the layer hierarchy, it's very important, but then also you can choose different components or processes and actually compare these different systems along all of these lines to get then an aggregate view of whether you can actually consider that systems to be relatively decentralized or not. So you can also create fancy maps with this, so you just pick any 2 variables or processes, and then you compare different systems against each other. So in this case, what we do is transaction processing or mining, and also the references. So what are these systems actually recording? And so what you can see is that there is a certain trend. So if you look at these open networks that are essentially socioeconomic constructs or socioeconomic systems that all have their native asset, which is why they are in the endogenous part there. But if you look at whether transaction processing is actually centralized or not, well, it really goes across the board. You have things like ODA, which have one single coordinator, so essentially there's no multi-party consensus. On the other spectrum, you have things like Bitcoin and Ethereum, which are relatively decentralized when it comes to transaction processing. And then you've got also these edge cases like Ripple, like Neo, Cardano, and so on, and Ethereum, that actually also can have hybrid references in the sense that because they have a fully functional programming language, they can actually create things that go beyond just a simple native asset like systems like Bitcoin, for example. And then what we can see, these closed networks, so you'll probably call them enterprise blockchains or permission blockchains, is that they are all kind of like situated in that left corner. So most of them are actually just recording things that are external to the system. So if you look at, for example, ASX, they are essentially just copying data from their centralized system onto a blockchain. So the data itself is really just a representation of data that exists in a different system. If you look at, what is it, at NASDAQ, it's pretty much the same thing. If you look at an IBM or whatever Walmart supply chain thing, they are just recording things that exist outside of the system. So they need to get it somehow on the system. There's no native endogenous thing there. Now, the Royal Mint goal would be different, which is why it's in the middle, because the token itself only exists within the system, can be considered an instrument on its own, essentially. But it's still hybrid in the sense that you need to rely on the Royal Mint gold to get your actual physical gold in exchange. Now, also one thing you can see is that they're all in the left corner, which means that we really had trouble actually finding a case study of an enterprise blockchain that has more than one single validator or record producer. And so we spoke to some of these projects, and actually right now what we can see is that most of these companies say that they want to be conservative, so start with a controlled environment, which in many cases means controlled by one single company, and then gradually over time distribute control over these systems. Now that is theory, so right now we've been waiting for 2 years. We're still kind of stuck in that corner, but then again, for enterprises, really, it's not like you're going to launch just another application, but here we're talking really about launching full stack financial systems in some cases, so that's not something where you want to move necessarily very, very fast. But so we expect that over time, this will move a bit towards the right, so that these projects, they will gradually distribute control to more and more members. So yeah, just to wrap it up, so what were the objectives of that report? So first, create a unified terminology, so at least define certain words, define what a DLT system is, so that people don't talk past each other anymore. And then second, provide a multi-dimensional tool that you can use to essentially analyze any given system, maybe use it even for system design as kind of like a checklist. And then, of course, to compare different systems to reveal these often hidden trade-offs. Okay, so what's next? Well, please share it, have a look at it with your colleagues or whatever, and then experiment with it. If you want to build a new system, just have a look at it. If you actually want to improve it, please do, and let us know. Actually, we'll be very interested in knowing if people actually come up with new processes, new configurations, remove existing ones. So it's an open source tool, so anyone can just like use it, build it, and use it for their purposes. I would say that's it. Are there any questions? Got very quiet. No? Oh, sorry. If I can just give... Does it work? Yeah. There you go.
Thank you very much for sharing your structure with us. At the very beginning, you had the 3 layers, the process layer, the network layer, and the data layer. Is that correct?
So protocol and network data.
Yeah, exactly. So if we talk now, for instance, of Hyperledger or Ethereum with the smart contracts, would you then put the smart contract part into the data layer? Is that correct?
Yes. Now, the thing is, there's different ways of having smart contracts, because some people would argue that Bitcoin itself has smart contracts as well, right? Although they're pretty limited to some extent. But a multi-signature contract in itself is a smart contract. So I would say when it comes to really the nature of these smart contracts, or what is the meaning behind that particular data or string of data, then that's definitely in the data layer. But when it comes to having native support for fully functional smart contracts that are understood at the protocol layer, which means that every node that runs the same software will actually understand what that contract means, then I would say it also fits back to the protocol layer in itself, that has native support for them. So there's a difference between whether there's native support, whether all nodes understand if they download that client implementation, so it's part of the protocol itself, which is the case for Ethereum, which is not the case for dApps on top of it, right? So not every Ethereum node actually understands what this dApp does, and it actually doesn't really care, which means that there the meaning and the nature of the data itself is rather specified in the application layer, which means that you probably have to run yet another node. If you have the example of Augur, for example, you need to run an Augur node in addition to actually understand what that data really means. A good example would be also Counterparty or Omni on top of Bitcoin. A Bitcoin node has no idea what that string of characters means in the op return field. But if you actually also run a Counterparty node or call it coin implementation, then you will understand what that data string means.
Okay, and the mempool, where would that be, for instance?
That's all part of the network layer. So the network is really how data is being broadcast. It's more like conceptually, right? So the thing, because all these things are intermingling, but it's more like from a conceptual point of view, how can we separate it? Because the main thing we actually want to do together is that there is a certain layer hierarchy, which tends to kind of get neglected so far.
Thank you very much.
Any other question? So the report is freely available, just like all our other reports. So please feel free to have a look. And if you play around with it, I would be very interested in knowing what comes out of it. So if there's no other question, I would say thank you very much, and yeah, thanks.